Video we start a new series of clips which is about Schur's theorem on integer coloring, right? So we have decided to do this in 6 parts, part 0 to part 5. Let's see. So I'll just give you the introduction, what is the theorem is all about, and we will prove finally. And we need some machinery to prove this, so we will be going through those tools in the early clips. Yeah. So suppose we have 1 2 3 4 5 6 k plus 1 up to n, so integers, positive integers, and one want to decided to color this all integers with finitely many colors. For example, suppose I have this many colors like violet, red, pink, or all these 3 colors. I am going to color all integers. So this is one kind of coloring, and of course it's very when I say I color all the integers, because they are positive integers are infinite, nobody can color all integers anyway. But suppose it is done, right? Some cases we can do that, right? For example, you color all odd numbers by blue and even numbers by red, then it is very clear that all integers are colored, right? And similarly, if you color all with red, then also we know that that is done, right? And right. So, but if you are going to color with different colors, as many the way you want to do that with a random process, then that is difficult to understand, or we cannot do that, being given a finite number of years to live. Anyway, so look at this coloring. So in this coloring, 1 4 5 has same colors, right? So, and you can add this up. If you add 1 plus 4, you get 5. So what is happened to this equation? This 1 4 5 has same colors, right? Yeah. So what is Schur saying? Schur's theorem is exactly the idea. If you color this positive integers is finitely many colors, right? You have finite number of colors and you want to color the all integers, then there exists a monochromatic solution. When I say monochromatic, that means all monochromatic solution to the equation x plus y equal to z. So that means x, y and z have same color. In this case, you get 1 4 5. We get a solution of 1 1 4 5, right? Here we have a solution 1 4 5. So such that 1 plus 4 equal to 5. So the triple has monochromatic. They all have same color. So that's why Schur saying, yeah, we have to prove it with right, yeah. So before we go for the proof will come in the part 3 or 4, I don't know. Before that, we need to develop some tools for this. So the first tool we need is a very beautiful one, which is called the Pigeonhole Principle, right? So let's go back to what is Pigeonhole Principle? What are some applications, right? So Pigeonhole Principle is a very basic theorem, maybe in all mathematics. Maybe I can say, because it comes out of a common sense, basically. So let n pigeon sits on or want to live or want to occupy, right, k holes. We can talk about a situation like this. Suppose there are k holes available. Maybe for numbers, suppose there are 3 holes in a tree available, and there are 5 pigeons, right? And suddenly a big rain comes up, then the pigeons has to occupy one of these holes, right? So the theorem says that there is at least one hole contains 2 or more pigeons, because there are 3 holes and you have 5 pigeons. So such a rain comes and they are forced to occupy one of these three holes, then what is the theorem says? The pigeonhole principle says there is at least one hole contains two or more pigeons. How do you prove that, right? So more generally, the number of pigeons has to be strictly greater than or equal to the number of holes, so that I can say like let n pigeon sits on k holes with n greater than or equal to k is a crucial assumption. Then there is at least one hole. At least one hole. There may be many holes. I mean more than one holes, such that it contains two or more pigeons. So this is a one beautiful picture I got from internet. So there are 9 holes and 10 pigeons, right? So this hole contains two fellows. It's very intuitive because this pigeon cannot occupy anywhere else. So, right? So they have to this pigeon here. He has to occupy one of the holes already occupied by a pigeon. So, right? Okay. You may have this pigeon. This hole is empty. Then that pigeon has to occupy somewhere else, right? So that hole will have. So that is intuitive. Now we go for formal proof. So what we are going to assume is all holes, right? All holes contains at most one pigeon, right? So n greater than or equal to k holes are there. Then suppose all the holes contains at most one pigeon. Then what happens is at most one means a hole can be empty also, right? So in the maximal case, suppose every hole contains exactly one pigeon, then the number of pigeons is exactly equal to the number of holes. So what I am telling is at most one, because that is an exactly the negation of what we have to prove. We have to prove that there is at least one hole contains two or more pigeons. So what I am trying to say, suppose every hole contains not less than 2 or 1 or less than or equal to 1, right? So then what happens is the number of pigeons is less than or equal to number of holes, right? That means n less than or equal to k, but we already assumed that n greater than k, yeah? So that is that's the problem. Okay, so that's a condition to n greater than k. So that's that easy to prove that claim. So one of the another more useful version of the pigeonhole principle is, in fact, we can prove more. I mean, there is at least one hole. I said 2 or more, but I can say maybe more. I want to say that it contains at least n by k, n over k, the floor of. I mean, the floor function is. You may be familiar with the floor function, because floor function means whenever you have a real number, floor function gives the next big integer greater than the greatest integer, the least integer greater than x. Right? For example, if you have 1.7, the next integer coming is 2. So that is your floor of 1.7. You know the ceiling is opposite. This is ceiling. I'm sorry. This is ceiling function. So floor is what we call greatest integer function. That means this is a greatest integer less than or equal to x. So normally if you have a real number, the next integer is your ceiling function, ceiling of x. Just before is, so you get the inequality very easily, right? Yeah. Anyway. So what I can say that if there are n pigeons and k holes such that n greater than or equal to k, then there is at least one hole contains ceiling of n by k pigeons, right? So that's what we can say. So floor is, you know that a floor is least integer greater than x, right? That means just after the integer comes just after x. That's the That's the idea. So 1.5 is 2, 0.1 is 1, and my negative 1 point is negative 1, because negative 1 is which is greater than negative 1.2, and that's integer. So assume, now we have to prove this, right? Assume all k holes contains less than these many pigeons. Okay, so what I have to prove? There are at least a ceiling of n by k. So if I say less than ceiling of n by k, so ceiling of n by k, suppose n by k is a fraction. I mean, suppose it is not an integer. Then I told you that for every number, you know, that is ceiling of this inequality is true. So suppose x is a real number, or n by k, x equal to n by k is a fractional number, and if I assume k holes contains less than ceiling of n by k, and being an integer, the number of the pigeons comes with a positive integers, right? So the next integer is, the next lowest integer is floor of x, right? So by assuming like this, suppose all k holes contain less than ceiling of n by k pigeons, that means there are less than or equal to floor of n by k. That is the idea. Okay, this is actually we need. All right, I need yeah. Okay, now let's so we assumed all k holes contains less than this. So the number of pigeons, we can say there are k holes. Now each hole contains m1, m2, mk pigeons. First hole contains m1 pigeon, second hole contains m2 pigeons, but this all mi's are less than or equal to floor of n by k, right? That's what we have assumed. So that means the number of pigeons is, so if using the inequality, I can replace m1, m2, mk by this upper bound, and n by k, floor of n by k. Now this floor of n by k is less than n by k. That's what I have already mentioned. So I can make an inequality, right, less than this. Okay, and right. So that means the number of pigeons is yeah, less than n. Yeah, so so you have to note that in this case we assume actually that n is not divisible by k. K does not divide n. It is because when k divides n, then the assumption would be is an integer, right? So there would be a change in the assumption, because when you say it contains less than floor of m by k pigeon, means less than or equal to floor of function. But if n by k is an integer, these both are equal. If n by k is an integer, then floor of x and ceiling is of equal. So that assumption has to change. So when n by k is an integer, some m, then it should be less than or equal to m minus 1, right? In that way, in both cases you can say. So right. So in this case, I assume k does not divide n. If k divides n, similar way you can prove, right? Then we don't have to use this floor and ceiling function. Okay. So in this case it is strict, because n by k is not divisible, so this is strict case, right? So you can use this. So what you prove is the number of pigeon is less than n. So same thing you can come up with. If n by k, k is divisible by n, then there is a little change in the assumption, n by k minus 1, right? All this this would be changes to n by k minus 1, and still you can prove that it is less than n. So that is a contradiction, because we have n pigeons, right? Yeah. So that's so the idea behind this. Now we can do some examples. What is the minimum number of people needed to ensure that there is always two or more people have same birth month? That means I have a group of people, and and there is a number of people of that, and what is the minimum number needed? What is the minimum number of people that I have to gather such that there always exists two people having same birth month? That means their birth month, suppose November, two people having November as a birth month or something like that. I'm not talking about November it's particularly. Okay, what is the minimum number of people needed? So you have to so the pigeons are people here, right? Holes are months. So there are 12 months. Let the number of people be n, right? So what is the pigeonhole principle says? Right, there are a number of pigeons and number of holes. Then at appropriate n and k, there is one hole containing two more pigeons, right? So that formula is basically floor of n by 12, right? So here we need two people needs to put into same month, right? So this has to be greater than or equal to 2. Floor of n by 12 greater than or equal to 2. So you can see that n is just greater than or equal to 13. Then 13 by 12 is 1.02. Then that the floor is 2. So if you put n equal to 13 people, then there are only 12 months. So the 1 month should contain at least two people. They have same birth month, right? Yeah. So 13 people are needed to ensure that, right? So minimum number of people. More than 30 people always, right? Yeah. Okay. So there are many versions of PHP. I mean, this is PHP means Pigeonhole Principle available, but for our need, this formula, this idea is sufficient, right? Yeah. So next we will do some graph theory and some applications of Pigeonhole principles in that. Okay. Thank you.